Welcome to this explainer. Okay, today we're diving into something absolutely fascinating, how artificial intelligence is radically accelerating the way we discover new drugs and advanced materials.
I mean, think about it. What if we could invent a life-saving drug without ever actually touching a test tube? For centuries, chemistry has basically been a science of trial, error, and physical synthesis, but modern computational chemistry has completely flipped that script. We are now simulating complex molecular interactions in a digital space way before a single physical experiment is ever run. It's literally rewriting the rules of scientific discovery.
Here's our roadmap for today. First, the virtual test tube. Second, rules of the simulation. Third, the quantum bottleneck. Fourth, AI enters the lab. Fifth, drugs, proteins, and materials. And finally, the autonomous scientific future. Let's get right into it.
All right, Section 1, the virtual test tube.
So if you've ever been around a chem lab, you know traditional synthesis is heavily bottlenecked by physical constraints. It's expensive, it's often hazardous, and man, it is painfully slow. By shifting the laboratory into a virtual environment, researchers totally bypass these physical limitations. We're talking about rapid, predictive modeling that lets us test thousands of iterations in the time it takes to run just one single physical assay. It's really all about maximizing the speed of innovation while cutting down the huge resource drain of traditional wet labs.
To really understand where we are right now, we kind of have to look at how this whole computational stack evolved. We started with rudimentary classical calculations, eventually moving into mapping atom-level electronics using quantum chemistry. And that paved the way for dynamic molecular simulations, which were then supercharged by high-performance computing. And that brings us to today, stage 5. We are in an era where AI doesn't just calculate chemistry, it actually predicts it. This allows us to screen literally millions of compounds in fractions of a second. It's a real game changer.
Moving on to Section 2, rules of the simulation.
Okay, so before we can simulate a reaction, we have to map what's called its potential energy surface. Basically, this lets us visualize exactly how and why a molecule changes its shape. But as you can probably guess, for complex molecules, this topographical map becomes impossibly vast. It dictates everything from transition states to deep stability pockets. Navigating this crazy multidimensional terrain mathematically, that is the foundational challenge that computational chemistry is trying to solve. To simplify all that vastness, we often use something called molecular mechanics, and it operates under a really simple assumption. Atoms behave like balls, and bonds behave like springs. It sounds basic, right? But this fundamental, classical assumption is absolutely crucial. It allows us to model massive biological systems rapidly, intentionally avoiding the immense, agonizing mathematical drag of computing complex quantum electron behavior. Now, these classical balls and springs assumptions form the foundation of what we call force fields. Think systems like AMBER or CHARM. They calculate exactly how these atoms interact, using strict mathematical rules for bond stretching, angle bending, torsional rotation, and even non-bonded stuff like electrostatic forces. Put it all together, and these components basically act as the physics engine for our digital molecules, calculating the trajectory of millions of atoms over time.
Which brings us to Section 3, the quantum bottleneck.
Here's the catch, though. When we need true atomic fidelity, like actually understanding chemical bonding, magnetism, or electron transfer, treating atoms like balls and springs just isn't going to cut it. We have to turn to density functional theory, or DFT. DFT applies quantum mechanics directly to electron density. It gives us unparalleled predictive accuracy for geometry and reactivity. But, and this is a big but, it comes at a massive computational cost, which severely limits the size of the systems we can even look at. The whole foundation of this accuracy relies on the famous Schrödinger equation. However, trying to calculate the exact quantum behavior for anything larger than just a few interacting atoms means hitting a massive mathematical brick wall. The computational complexity just scales exponentially with every electron you add. Because of this, researchers are forced to rely on heavy approximations just to make the equations solvable within a realistic time frame. And honestly, even when we throw massive high-performance computing resources at the problem, I'm talking world-class supercomputers, huge computing clusters, and immense parallel processing setups, simulating just a few microseconds of a large-scale system can still take weeks or even months. So despite having our absolute best hardware on the job, we still face this really severe computational bottleneck that just slows down discovery. All right, Section 4, AI enters the lab. So, This is where the massive paradigm shift happens. Instead of brute forcing those complex physics equations from scratch, machine learning just bypasses the math entirely. By training on vast data sets of previous quantum calculations, AI models can instantly predict molecular energies, electron distributions, and reaction outcomes. You see, they predict the answers rather than calculating them step by step. This cuts computational costs by orders of magnitude and unlocks scale like we've never seen before. In fact, machine learning optimizes virtually every single step of the computational pipeline. It enhances the accuracy of our force fields, it dramatically speeds up molecular dynamic sampling, and it can even predict exactly how an organic chemistry reaction is going to unfold just by analyzing activation energies. This completely, fundamentally transforms how we rank viable candidates when we're dealing with really complex molecular docking scenarios.
Let's see how this is applied in Section 5, Drugs, Proteins, and Materials. Let's ground this in reality for a second. In biology, a primary amino acid sequence is really just the starting point, right? A protein's true biological function is dictated almost entirely by its complex 3D folding. Well, AI models have revolutionized our ability to rapidly and accurately predict these tertiary and quaternary structures. It instantly unlocks deep structural understanding that, honestly, used to take researchers years of painstaking X-ray crystallography to figure out. And all of this structural data feeds directly into computational drug discovery. AI seamlessly moves us from initial virtual screening straight to predicting the exact molecular docking orientations between a drug and its protein target. By simulating things like absorption, distribution, metabolism, and toxicity, what we call ADMET, super early in the pipeline, it slashes development costs and makes absolutely sure that only the most viable, highly optimized leads ever make it into a physical lab. But hey, this intelligence isn't just isolated to medicine. AI is simultaneously out there screening thousands of candidate nanomaterials to help design the physical infrastructure of tomorrow. We're talking about predicting the conductivity of new alloys, modeling exact surface behaviors for advanced solar cells, and even designing next-generation batteries. Machine learning is literally accelerating material science across the entire board. Which takes us to our final stop, Section 6, the autonomous scientific future. Things are getting pretty sci-fi here. We are now seeing the creation of digital twins. These are highly accurate, holistic virtual representations of complex chemical reactors, advanced materials, and even intricate biological systems. Having these virtual mirrors allows engineers to continuously optimize manufacturing processes, stress test environmental variables, predict maintenance needs, and mitigate massive risks, all entirely in a computer, long before a physical counterpart is ever built. And the ultimate endpoint of this convergence, a fully autonomous scientific workflow. We're looking at AI systems that are now capable of forming their own novel scientific hypotheses, then automatically running complex simulations using supercomputers, rigorously analyzing those results through machine learning, and then, get this, continuously generating the next set of hypotheses. This unsupervised loop is accelerating innovation at an unprecedented scale. It's almost mind-blowing. So, as explainable AI and continuous digital molecular design become the new normal, tomorrow's chemists aren't just going to be running routine experiments. They're going to be orchestrating massive, automated intelligence systems. Which leaves us with one final, pretty profound question to consider. As these self-driving labs grow more advanced and entirely self-sufficient, will the next great Nobel Prize-winning chemist even be human